Hi, my name is Meenakshi Sundaram and I am an application engineer working for Cypress Semiconductors at Chennai, India. I am going to show you a motor control demo using the third generation Cypress Programmable System on a Chip or PSoC. This PSoC has a 8051 microcontroller and programmable digital and analog blocks to create an entire system. The demo uses the development kit called PSoC DVK. To know more about PSoC and the DVK, please visit our website at www.cypress.com. The motor which is being driven in this demo is an 8-pole 26-watt BLDC motor. The algorithm we have implemented can drive a permanent magnet synchronous motor or PMSM for short, or a brushless direct current motor or BLDC for short. The only modification required is to have the appropriate driver board that can support the wattage rating of the motor and an appropriate two-phase current measurement circuit to measure the maximum current consumed by the motor. The demo uses field-oriented control or vector control. I will refer to this as FOC. FOC is one of the methods used in variable frequency drives or variable speed drives to control the torque and thus finally the speed of a three-phase AC electric motors by controlling the current fed to the machine. The major advantage of FOC over other methods is that the rotor is monitored at every position and the algorithm ensures that the rotor magnetic field and stator magnetic field are always aligned at 90 degrees to each other. As a result, the torque or the tangential force is at its maximum. In order to achieve this, precise real-time position information of the rotor is needed. The demo uses the Hall sensors to measure the speed of the rotor. The position of the rotor is calculated by accumulating this speed over a period of time. Hence, this demo shows sensored FOC. A single FOC loop, including the current measurement, speed update, and PWM generation, takes about 200 microseconds. For more details on timing, please refer to the application note we will be publishing soon. Okay, now let's move on with the demonstration. First, the potentiometer, which controls the speed, is brought down to 0 position to avoid huge startup currents because of the high speed ramping at the start. SW1 of the PSoC 3 DVK is being used as stop and start switch in the project for starting and stopping the motor. Reset button in the DVK can be used to reset PSoC 3 if needed. To begin the demo, first the SW1 is pressed to start the motor. The speed is then raised slowly. The motor will pick up the speed once the minimum torque required to rotate the motor at no load is reached, and the generated PWMs thereafter reach the MOSFET switches in the motor driver board. Now you can see the motor rotating. For more lively information on what is going on, PWM duty cycles generated for the two-phase legs of the MOSFET switches have been tapped out and is displayed in the oscilloscope as you saw. Now I will show you how the speed of the motor varies by changing the potentiometer value. As you can see, the frequency of the waveforms is nothing but the electrical frequency of the motor. Electrical frequency means the rate at which the motor coils are commutated. In this demo, it is 4 times the mechanical frequency or speed of the motor because of the presence of 4 pole pairs. Let us see how this change is reflected in the motor. You can see how the motor speed varies as I vary the potentiometer, like the frequency of the waveform in the oscilloscope. You can see it's coming down and then it's moving slowly up. So that's it. Now I'll bring the speed input to 0 slowly. Then press the stop switch. Yeah, the motor is stopped. Thank you for watching.